Okay, in the last lecture, we have seen the residue theorem that is helpful in calculating the contour integrals. So we'll continue and essentially revolved around the application of residue theorem. Rest of the complex analysis essentially revolved around the application of residue theorem to various type of integrals. So let's go ahead and first remind us about the residue theorem once again very quickly, then go on with some examples. So we will look at some of the examples of a residue theorem. This is a part of the course PH3103 at IISER Kolkata. Let's quickly remind ourselves of residue theorem. The residue theorem essentially states that if you have a domain in which function f of z is defined and you want to take the contour integral over a contour C in this domain. The contour C is simple closed curve, and inside the contour C we have a finite singularity at Z1, Z2 and so on till Zn. Then the integral of a function f of z over this contour C is given as 2 pi I times the sum of all residues of the singularity inside this contour. So it's a fairly straightforward theorem and very easy to apply. We have some failure of special effects here. So let's take the first example. We are trying to evaluate the integral f of z is equal to 1 by 1 minus z square minus z minus 3. So we have seen one of the similar example, but in this case the contour is different. In this case contour is given mod z is equal to 2. It is a circle with the radius 2 around the origin. So we have already seen that it has two singularities. At z is equal to 1 we have a second order pole, and at z is equal to 3 we have a simple pole. So let's try to plot them. We have two singularities at z is equal to 1 and at z is equal to 3, which is simple pole. Our contour in this case mod z is equal to 2, which is a circle of radius 2 around at origin. So we clearly see that the z is equal to 3 is outside this contour and we need not worry about. So we have to just need the residue at the point z is equal to 1. We have computed this in the last example itself, and the residue at the point z is equal to 1 is a minus 1 by 4. It's a simple exercise. For the pole of the order 2 we can straight away substitute and obtain. And the integral f of z is equal to 1 by z minus 1 square into z minus 3 over the contour mod z is equal to 2 is given as 2 pi into residue of 1. This is equal to minus pi by 2 into I. So this is how we use a residue theorem. Let's take one more example. We call it an example X. So we are not Roman, so it's not 10th example. We just say that X is some arbitrary number. In this example, we evaluate the integral f of z is equal to 2z plus 6 divided by z square plus 4. The contour over which the integration is taken is a mod z minus I is equal to 2. That means it is circle of a radius 2 shifted in the positive direction along centered around z is equal to I. Let's look at the singularity of this function. We can write f of z as 2z plus 6 divided by z minus 2i into z plus 2i. It is clear that it has two simple poles at z is equal to plus or minus 2i. So we have to evaluate the integral around this. Geometrically, let's look at both contour as well as singularities. We have two singularities at z is equal to plus or minus 2i. And we have a circle which is centered around z is equal to plus I with the radius 2. So this simply excludes the singularity around minus 2i, and within our contour we have only one singularity at z is equal to plus 2i, and we have to compute the integral. So let's compute the residue. Both are simple poles, so all we have to do is multiply it by z minus z naught into f of z and take the limit z going to 0. So let's compute the singularity for minus 2i. So it's not necessary for this problem. However, as an exercise, you can do it. We have not done much example for computing the residue. So you use this as an excuse to compute the residue. So you can find out that the value of residue at z0 is equal to minus 2i is given as a 1 plus 6 by 4i. In the same fashion, you can calculate the residue at plus 2i2, and that turns out to be 1 minus 6 by 4i. So now we have a residue. We can simply compute the integral over this contour, and we see that the only one singularity is inside. So we have a contour integral 2z plus 6 divided by z square plus 4 taken over the contour z minus I mod equal to 2 is given as 2 pi I times the residue of f of z at 2i, that is equal to 2 pi I into 1 minus 6 by 4i, and that is equal to pi times 3 plus 2i. So this is a value of integral. In general, it's a complex number, and that is what you get as an integral in the complex plane. Now it is a time for a homework problem. So this is to evaluate contour integral of a function f of z is equal to e to the power z divided by z to the power 4 plus 5z to the power 3 using the residue theorem. The contour over which this integral taken is a circle with the radius 2, that is mod z is equal to 2, centered around the origin z is equal to 0. The procedure taking the contour integration is first look at the function and compute the singularities, draw the contour and place the singularities in your z plane, and see how many singularities are inside the contour and how many of them are outside the contour. You don't have to consider the singularity outside the contour, and then you can evaluate the residue for the singularity inside the contour and then use the residue theorem for computing the integral. Now let's take one more example, get some exercise. Let's evaluate the contour integral of tan z dz over the contour mod z is equal to 2. So this is a circle with the radius 2 centered around origin. Now let's find out the singularity of this function f of z tan z. We write it as a sin z by cos z, and then we have a singularity when z goes to cos z goes to 0. But when we look at our interval, we have only two values over which cos z goes to 0, that is at z is equal to plus or minus 2 pi. The rest of all the points are outside our contour, and we do not have to consider. Let's try to evaluate the residue. Before that, we need to see what kind of a singularity this function has at z is equal to pi by 2. So first we have to see what kind of a singularity this function tan z has at z is equal to plus or minus 2 pi. So evaluate, we write tan delta z minus or plus pi by 2, and that can be written as tan delta z minus or plus pi by 2 divided by cos delta minus plus pi by 2. This simplifies to minus cos delta z by sin delta z. As delta z goes to 0, we see that this has a simple pole at z is equal to plus or minus pi by 2. You see that the cos tends to value 1 and the sine function has the simple pole. We know that sine expansion starts with z minus z cube by 3 factorial and so on. So this simply indicates that the sine function has a simple pole at x is equal to 0. So with this we see that the tan z has a simple pole at z0 is equal to plus or minus pi by 2. Now we have to compute the residue. Using this equation itself, we can compute them. We already have indirectly found it. You can multiply it by delta z and simply take the limit delta z going to 0. Delta z is our z minus z naught, and we see that we get the residue as minus 1 for the both these values. At z is equal to plus or minus pi by 2, we get the residue to be minus 1. Now we can compute the integral over the contour C tan z dz is equal to minus 4 pi I. One more example. So we have to evaluate the integral e to the power 3 by z dz over the contour C, which is described by a unit circle around the horizon. Here the contour C is the unit circle over the origin. Now for this function, first we have to see if there is any singularity. We clearly see there is a singularity at z is equal to 0. Now is to see what kind of a singularity it is, simple pole or pole of order n or whatever, and then compute the residue. So first we have to expand this in terms of a series. Seems to be a rather difficult to do for the e power 1 by z. So instead we take the first Taylor expansion for the function f of z is equal to e power z, which can be written as n going from 0 to infinity z to the power n factorial, or 1 plus z square by 2 factorial plus z cube by 3 factorial and so on. So this is a simple expansion for e power x. Now replace this z by 3, and then we get the expansion from e power 3 by z. So this looks like somewhat a cheap magical trick, but it does indeed works out. And expansion for e power 3 by z is given as a 1 plus 3 by z plus 3 square by 2 factorial into z square plus 3 to the power 3 divided by 3 factorial z cube and so on. By looking at this, we clearly see that the series does not terminate, so we have an essential singularity at z is equal to 0. But the residue theorem can be applied for any isolated singularity. We do not have to worry the nature of singularity. As long as it is isolated singularity, we can simply compute the residue and get the value. So from the expansion itself, we can pick up the residue. So we see the coefficient of 1 by z, that is residue, is equal to 3. So integral e to the power 3 by z dz over the contour mod z is equal to 1 is given as a 2 pi I into residue of f of z is equal to 0, that is equal to 6 pi I. Now we can have many more examples, but we will connect it to problem which we are interested to evaluate the integral. So far what we have done in this class is that we have just treated it as a mathematical problem and evaluated the integral. This is rather a boring exercise, mechanically doing this problem. So we will get some physics and geometry into this and try to solve a few more problems in the coming lectures. Now we'll stop here.